This example problem involves one-dimensional spring and truss elements. Let's go ahead and get started. So what we have given is we have one truss element connected between two rigid supports and two spring elements, a force at one end, and here in node 2 we're going to go ahead and say that's fixed. What we want to do is we want to be able to find the displacement at all the nodes, really the only movable nodes, which is node 1 and node 3, and we also want to be able to figure out what the force is through each element and the reaction force here at node 2. And the solution involves the same steps that we've seen before. First we need to put together the element stiffness matrices. Then we assemble the global stiffness matrix from those element stiffness matrices. And then once we do that, we go ahead and apply the constraints to that global stiffness matrix, and we create our reduced matrix equation. Then we apply our loads, solve for the results, the displacement results, and then we use those displacement results to solve for the reactions. In this case, it's just the reaction there at node 2. And then we can also solve for the elemental results. In this case, the forces going through each of the spring elements and the truss element. Okay. So we start with part 1, which is the element stiffness matrices. Drawing our whole item again, and we go ahead and take a look at element 1 right here, and we take a look at element 2 right here. Just our basic spring stiffness matrix equations. And then we also take a look at element 3. Note that element 3 connects nodes 1 and 3, and so we're careful to illustrate that in our equation there. Okay, so then we go to the global stiffness matrix equation, and we just assemble that using the element stiffness matrices that we have. First, we're going to go ahead and write in the placeholders for the global stiffness matrix equation. We have all the nodes, which turn out to also be the number of degrees of freedom, since this is just in one dimension. And here we're just going to go ahead and add in the stiffness matrix for element 1. Element 1 connects node 1, node 2, degree of freedom 1, degree of freedom 2, and so that's why we go ahead and put it right here. Then we go ahead and look at element 2 connects nodes 2 and 3, and so you can see that's where those stiffness values go. And then finally we have element 3. Element 3 connects nodes 1 and 3, and so that's where those stiffness values go. All right, so now we go ahead into the next part, which is applying the constraints to create our reduced matrix equation. There is our global stiffness matrix, and we recognize that node 2 is fixed. It's 0. So what we do is we take away the column and we take away the row that correspond to node 2. And that gives us our reduced stiffness matrix equation for the whole system. And at this point, the only thing left to do is apply the nodal loads and solve for the displacements. Well, that's where we can actually solve. Once we get the nodal displacements, then we can go ahead and solve for some other things. But the first thing we have to do is solve for those nodal displacements. So we go ahead and write in our reduced matrix equation. So that's the global matrix with the constraints applied and the corresponding rows and columns corresponding to that constraint removed. We go ahead and plug in what our value is for our loads. So in other words, we don't have any load applied at node 1. We do have a load applied at node 2. It's going in the negative x direction, and so that's why we have the negative sign there. And then that's our general matrix equation format. We can go ahead and solve for this by simply inverting this reduced stiffness matrix over the other side, multiplying against our forces, and that turns out to be our displacements. So once we have our displacements, then we can go ahead and solve for the reactions. In this case, it's just the reaction there at node 2 that we're interested in. We'll go ahead and write in our global matrix equation. We're going back to the global matrix, writing in all those aspects that we have for that, all the different stiffness values there. And previously, what we did with the global matrix is we reduced it, and then we applied the known loads and solved for the displacements. So now we know what the displacements are. We're going to use these displacements. We're going to plug these in to solve for our forces. We know that node 2 has no displacement, it's fixed, and these are known, and so we can go ahead and solve for all these forces. Now this is global force vector, which means that it contains all of them, the applied loads and the reactions. So This is our applied load, that's our reaction. And if we want to just figure out what the reactions are, well then we just take our global load vector that we solved for and then just subtract what's applied. Now we can go ahead and solve for the elemental results. And in this case, we go to the elemental matrix equations. So we go ahead and write these in again. There's our elemental stiffness matrix equation for element 1. There's our elemental stiffness matrix equation for element 2. And there it is for our truss element, element 3. And once again, just want to remind you that we do know what these values are. We do know what the displacements are, and so we just plug those in. And then we solve for our elemental results. We're solving for the forces still. And we want to make a note here. We want to make a note about what's happening. So when we look at a element here, this is a spring element. When we look at a spring element, remember that at each node, when it goes to the right, we typically consider that to be positive. However, when we look at the element itself, we consider it to experience a positive force when that force is tensile. Okay, so what happens? Well, we want to make a note that at node 2, at the second node defined in that element, what is considered positive at the node is also considered positive for the element. And so that's why, and vice versa, that's opposite. That's why when we go ahead and eventually solve through to get our force values for the spring element or the truss element, we're going to get two values. These values are going to be equal and opposite. They have to be. It's a static situation. But the equal and opposite values correspond to the fact that it's considered positive at the nodes if it's going to the right, but for the element itself, it's considered positive if it's in tension. And so that means on the left node, or the first node defined, it's going to be going in the left direction, and the right node, or the second node, is going to be going in the right direction. And so we just want to emphasize that it's the second value in that vector that is what the element is actually experiencing. Okay, so now we have some reflection questions. The first reflection question is, what is the stiffness K for the truss bar element? The next question is, why were the truss element stiffness components not adjacent to each other in the global stiffness matrix like they were for the spring elements? And finally, what would the reduced stiffness matrix look like if nodes 1 and 2 were constrained instead of what we had in this example where just node 2 was constrained? And that concludes our example with the 2 spring elements and the 1 truss element in a one-dimensional FEA problem.